Okay, these four equations require the properties of logarithms. So, for example, we need to combine these two logarithms into one single logarithm. And if you are adding two logs of the same base, which we are, you can rewrite them as one log, and you take and you multiply the x squared minus 6 and you multiply it by the 6. So addition is linked to multiplication. So that's the same as ln of 6x squared plus, or I guess it's minus 36. And that is equal to the natural log of 60. And now on the left side and on the right side I've got a natural log, so I'm going to ignore the natural log and I'm just going to focus on the 6x squared minus 36 equals 60. And because I'm missing the bx, so it's a quadratic, I've got an ax squared plus bx plus c. I've got no linear terms, so I'm just going to undo by inverse operations. So I'm going to plus 36 plus 36, so I've got 6x squared is 96 divided by 6 divided by 6. X squared is equal to 16. So now I'll undo the quadratic. So I know what my exponent is, so I can undo it. Inverse of a square is a quadratic, square the root that, and so x has got to be a plus or minus 4. Okay, the next one, kind of the same except for subtraction is going to be linked with division, but this time on the both sides we had a log, but on this side all my logs are only on the left, so it's going to be a little bit different. Log in base 7 of x squared plus 3, and you're going to divide that by the second one. Subtraction is linked to division. And then on the right hand side I just got 2. And you're done. You're as far as you can go. So your x's, or what you want to solve for, is kind of hooked up with the log, so we need to get rid of the log. We need to do the inverse of a log, so we're going to do exponent. We're going to morph it to an exponent, to a power. So your base in this power, your base is going to be 7, and the exponent is this, because the logs always spit out exponents, so it's going to be 7 squared equals x squared plus 3 divided by 3. So I've got 49 is equal to x squared plus 3 divided by 3. So now I can undo this by inverse operations. Pretty easy. Times both sides by 3, times this side by 3. 49 times 3. 147 is equal to x squared plus 3. And now do the same. I've got no linear piece, so I'm just going to minus 3, minus 3. 144 is equal to x squared. Undo the square, square root, square root. So x is going to be a plus or minus 12. Okay, now the bottom two are their powers. So I want n all by itself. I got to undo this minus 3. I got to undo the base of 14. I got to undo this. First I'm going to undo times by negative 7. So I'm going to divide by negative 7, divide by negative 7. So 14 raised to the n minus 3 equals, it's going to be a positive 27ths. Now I got to undo the base of 14. So to undo a base of 14, I'm going to do logarithm of base of 14. This is going to go here, and my exponent goes here. So now I got to use a calculator to convert this to some kind of decimal, approximate it to a decimal. So log in base 14 of 27ths. And that's approximately 0.398 is equal to n plus a negative 3, n minus 3. So now you just got a plus 3 plus 3. So it's going to be 3.398, somewhere around there. And this last one is similar. So let's undo the subtract 10. So plus 10 plus 10. So I got 13 raised to the k plus 10 is equal to 82. So now I got to undo a base of 13. So it's going to be log and base 13 of 82 is equal to k plus 10. Change this to a decimal. Subtract 10 minus 10. And k should be equal to, let me punch that in. So it's going to be log and base 13 of 82. And then subtract 10. And we get k is approximately a negative 8.28, somewhere around there. So express the solution to 4 to the 2t equals 6 as a logarithm. Okay, now t is with 2 and an exponent, so we got to undo the base of 4. So you got to do a log. It's going to be log and base 4 of 6 is equal to 2t. Divide by 2, and there you go. But then when you go to match it up with A, B, C, D, none of them show up. And then you're kind of in trouble. But what they've done is they have changed the base on you. And they've changed it to a base of 2. So we've got a base of 4. So there's kind of two options. You can use the change of base formula, or you can change this base right now. Because you can change from base 4 to base 2. It's pretty slick. It's just exchanging a 4 for 2 squared. So if you exchange a 4 for 2 squared, that is going to be 2 squared to the 2t, and those you need to multiply, so it's going to be 2 to the 4t is equal to 6. And now it's going to be log in base 2 of 6 equals 4t. And then divide by 4, so t is equal to log in base 2 of 6 divided by 4. Or times by a fourth. Okay, now the other way, if you change the base yourself, so it's log in base 4 of 6 equals 2t. If you change from base 4 to base 2, it's just going to be log in base 2 of 6 divided by log in base 2 of 4. And then this log in base 2 of 4 is actually that's pretty easy. So they're asking you 2 raised to what power is a 4? And this is a 2, so I can replace this with a 2. And then if I undo the times 2, if I divide by 2, that's like times them by a half. And times your denominators, that's going to be log in base 2 of 6 over 4. Okay, now the same type as problem as we did at the very beginning. We're given a formula, given some information, just plug it into the formula and see if we can find what they want. So A is the initial population, T is hours, and E is just your natural number. So the number of the model's natural growth. Find how long it's going to take for 200 bacteria, so I think that's our A, our initial population, to turn into 40,000. 40,000, that's going to be our total. That's the population as a function of time, so depending on hours. So let's go 40,000 is equal to the initial 200 multiplied by E to the 0.3 times time in hours, and that's what we don't know. So solve for T. Undo this, undo this, undo this. Divide by 200 first. Divide by 200, so is that 200 is equal to E raised to the 0.3 T. So now I gotta do logarithm. So it's going to be log in base e of, let's see, log in base e of 200, and that's going to equal 0.3 t. So if I want to solve for t, just divide by 0.3, divide by 0.3, and then on your calculator, just do the natural log. Natural log of 200 divided by 0.3, and I get pretty close to C, approximately 17.66 hours. An exponential equation is shown, drag and drop so that it is equal. So first, I'm going to divide by 3, divide by 3. So I've got e to the 4x is equal to 3. So I want to solve for x, but x is hanging out with a base of e, so I've got to undo it. So I'm going to do log in base e of 3 equals 4x. Now divide by 4, and log in base e is the same thing as ln. So x is going to equal ln of 3 divided by 4. Alright, so x is equal to ln 3 goes here. Divide by 4 is the same as multiplying by a fourth. So you could drag and drop just like that. 1/4 times the natural log of 3. When is the exponential function closest to 60,000? So 60,000 is the function based on x. So 60 grand is equal to 400 times 2 to the 0.3 times x. So I'm going to divide by 400. 60 grand divided by 400. 150 is equal to 2 to the 0.3x. So now morph it to a log. Log in base 2 of 150 equals 0.3x. Divide by 0.3, divide by 0.3. So log in base 2 of 150 divided by 0.3, and that's going to match up with D, pretty close to 24. Okay, which represents the solution to this? Now your variable's in an exponent. So let's undo the times 5. Let's divide by 5, divide by 5. So we got 3 to the 2x is equal to 4. Now you got to undo the base of 3. So we got to do log in base 3 of 4 equals 2x. Now to solve for x, you just got to undo the times 2. Divide 2, divide 2. Okay, so they've already got them. Log in base 3 of 4 divided by 2 is going to be the same as a half times log in base 3 of 4. So match that up with D. Now the last one, this one was the tricky one. These come from your Sage practice ones. We're given a model, we need to plug things in, but the population is in thousands. It's measuring it in thousands. So here we go. P is the population. Oh, something's wrong. So you're gonna swap 600,000 in for P, but because it's measuring in thousands, you're only gonna put 600 in place of P. So 600 equals 130 times e to the 0.09 times t, and t is time in years. So let's undo the times 130. Let's divide 130, divide 130. So 600 divide 130. That's going to simplify to 60/13 is equal to e to the 0.09 t. Okay, now let's undo this base of t, or this base of e. So let's do log in base e of 60/13, and that is equal to 0.09 t. And then let's undo the 0.09, so divide by 0.09, divide by 0.09. So on my calculator, do the natural log of 60/13, and then divide that by 0.09, and I get t time equals 17 years. So now if I add 17 years to 1995, I get 2012. Okay, last one is kind of like a bonus type problem. Let's take it piece by piece. This first piece, 3 multiplied by the log in base 2 of 64. So it's asking, log in base 2 of 64 is asking you 2 raised to what power equals 64? And I think it's 2 to the 6th. 2 to the 6th gives you 64. So this is log in base 2 of 64, that's really a 6. And a 3 times a 6, that's an 18. Okay, the next chunk, e raised to the log in base e of 5. If we undo this, it's going to be log in base e of what is equal to the exponent, and the exponent is log in base e of 5. So now your log and base e's are the same, so x is equal to 5, so this is a 5. And then log and base 1/3 of 9, it's asking you 1/3 raised to what power is going to give you a 9. And I think that's a -2. Because 3 to the -2 is 1/9, because 3 squared is 9. So 1/3 to the -2. So 18 plus 5 minus 2 is, this should all end up at 21.